That's me in 1985 when I was the manager of an AI center. So I've been in this field for a long time. Hopefully I haven't changed too much. And these are the books you mentioned that are translated in Chinese. Okay, so I'm going to talk about human parity. It's an excuse to talk about the state of artificial intelligence. Now, you see these announcements. I put some of the announcements more or less recent, where different companies claim, hey, my system has reached or even surpassed human performance, and in particular in natural language. And this is a more realistic diagram that shows you not surpassing, but getting closer and closer and closer. And that's another one. This is probably the most significant, where so all of these claims are based on some kind of benchmark. There's a test, you do the test, and you see how well your system performs compared with the average human. And this diagram shows that in almost all of these benchmarks, now there are systems claiming to have surpassed human performance. Human performance is 0-0 there. So has AI reached human parity? Well, the short answer is no. But my speech doesn't end here. It's a way to start a conversation about the real state of artificial intelligence. So we'll examine some of the most successful technologies that AI has introduced in the last few years. So I'll start with robots. The most popular kind of robot is the self-driving car. It's supposed to be actually the most high-tech robot. Why? Well, because cars kill people. In fact, cars kill about 1 million people every year. So it's very important that they become the best possible robot. In 2012, Sergey Brin, co-founder of Google, predicted that we will have self-driving cars available for the general public within 5 years. So in 2017. Well, 2017 came and went, and we still don't have them. Uber started delivering with a self-driving truck in 2016, and it's still a rarity. It's still used only in some special neighborhoods. In 2017, one of the many studies, this was a major study by the OECD, one of the major studies that came out, estimated that the 4 million truckers, more than 4 million, will lose their job in 13 years. And so there were all these studies and a little bit of panic for all these truck drivers who will lose their job. So this is another example of a headline: millions of drivers will be replaced by self-driving vehicles. So how many truckers lost their jobs to self-driving trucks? Zero. As far as I can tell, zero. I couldn't find one case. So that's the situation in 2022. In fact, this is a recent article where they discuss a shortage of drivers. We need about 50,000 drivers, truck drivers in the United States. And then I looked for the average salary of a truck driver in the United States. It went up dramatically. It's now $74,000 a year. And the average salary in the United States is probably now it's about 60. So they make more money than the average. Well, so much for the prediction that they would be replaced very, very quickly. Now, every year, there's announcement of progress. I mean, last year, a few months ago, Walmart started transferring goods between a warehouse and a market using self-driving trucks in Arkansas. And Too Simple, Silicon Valley startup, started deliveries from Tucson to Phoenix. Now, each of these is a very interesting experiment. All of them have a safety driver in the truck. So it's not really true that they are self-driving. Yeah, they are self-driving, but they are supervised by a human being. And only in some geographic areas. So the truth that they're not replacing the traditional truck driver yet. There are 0 self-driving cars operating on US roads that are completely autonomous. Actually, another study showed the whole point of the self-driving car was to reduce the number of accidents, right? They told us the self-driving cars will be safer than human drivers. And I do believe that many accidents caused by human drivers could be prevented by machines. But right now, this study showed 9.1 crashes per million miles driven versus 4.1. 9.1 is the self-driving cars. 4.1 is the human drivers. So they even make more accidents. Google Waymo's self-driving cars, there are only 1,400 in operation. They've been involved in 18 accidents in 20 months. As you probably know, 3 Tesla drivers have been killed in accidents when they were using the autopilot without paying attention. And there are studies that also self-driving cars may cause problems of several other problems. Anyway, so last year we were joking, instead of calling it a self-driving car, we're calling it the self-crashing car. That's a bad joke because people lost their lives. So that's the most popular robot. And then there are robots in construction, a robot in hospitals. And COVID-19 was a test for many technologies. And I didn't see robots helping much. Who built the one hospital in 10 days? Humans. And who's taking care of sick people in hospitals? People. In fact, all over the world, even in the most developed countries, we don't have enough nurses, let alone doctors. We just don't have enough nurses. And it would be great to have these robotic nurses that we have seen publicized for years. And in practice, this COVID pandemic was a test, and the robots failed us. In general, AI has been pretty useless in this COVID pandemic. So the pandemic, as tragic as it is, was also a way to test our technology, and AI, in my opinion, didn't pass the test. So not even right now, we really depend on humans for this kind of emergencies. Now, that's robots. Now let's get into software. Before I get into the software, the current software of AI, I always have a preamble, a warning that today, when we talk about AI, we're really talking about deep learning, which is just one of the many things that artificial intelligence has explored. It's been very successful in many ways, and that's why we focus on deep learning. But it's not the only one. So that's to avoid the idea that deep learning is certainly the solution to artificial intelligence. Maybe. Now, one slide, the history of deep learning. Convolutional networks actually date from at least 1989, when Jan LeCun developed LeNet-1. So let's remember, 1989, that's quite a few years ago. Then the solution to having many layers really came in 2006, 2007 with Geoffrey Hinton and Joshua Bengio. And most likely the people who are listening right now are very familiar with these legendary names. Now, the year when deep learning became very popular is 2012, right? 2012 is when a deep learning system called AlexNet, developed by Hinton's team, improved dramatically the accuracy, lowered the error in recognizing images on the ImageNet test. And since then, deep learning systems have further improved until they outperformed humans on several tests. So 2006-07 the theoretical model is fixed, 2012 is when it becomes very popular. By the way, AlexNet had 8 layers. 2012 is also when this team, Google Stanford team, showed us a system that could recognize cats in YouTube videos. I mentioned this because if I have time, I'll say something about this event that happened 10 years ago. So 2012 is the year when deep learning became very popular. It's important to understand why it took 6 years, from 2006 to 2012. Why? Because we still live in that age. So it took 6 years because deep learning needed 3 things. One, computational power. And luckily, for the market of video games, companies like NVIDIA were developing GPUs, very powerful processing units. They matured exactly when deep learning needed them. Then datasets. Deep learning, as you heard in previous talks, needs datasets. It's trained based on datasets. So we need very huge datasets like ImageNet that was developed by FAAI. And then software platforms made life a lot easier. So I always say that these are the real heroes of deep learning. These are the data sets used in the 90s, 2000s, and then it skyrockets. Then now we have so many, I would need 10 or 12 slides to tell you all the data sets that have been prepared, mostly by students in university like Stanford. And then the other heroes, the GPUs. So this is a historical picture of, I think, many years ago, 7 years ago. And today GPUs are even a lot faster than this. And then the platforms, which are not very famous, but they were also very important to enable more experiments in the lab. So the state of the art today is that we have different kinds of deep learning, and convolutional neural networks have been successful in face recognition, object identification, disease detection, as you see in the previous talk. We can discuss how accurate, but definitely there's been a lot of progress compared to the situation before. RNN, LSTM have been successful in speech recognition. You probably all use some kind of speech recognition today, translation, many other fields. GANs have been very successful in image generation, deep reinforcement learning, game playing, and today, foundation models, and I will get to foundation models. I have this slide that I keep updating every 10 years. Every decade seems to have a major new paradigm in artificial intelligence. So the previous decade was the decade of the GANs, very popular. And this decade seems to be the decade of foundation models. So we see how well these things are helping humans. So as I said, in image recognition, now systems outperform humans. This is ResNet from Microsoft in 2015. I think it was the first one to outperform humans. How? Very deep learning. So ResNet had 152 layers, and then there was another evolution of ResNet with even 1001 layers. So these are very complicated, very complex neural networks. I could list a lot of them. Okay, I stopped there. Just tell you the historical ones, and then you can imagine how much progress there has been over the years. What's the main issue with the very deep learning? Deep learning is highly unnatural. That's not what humans and animals do. For example, we don't need to see thousands of images of bananas to learn what a banana looks like. You see one, and you pretty much know what a banana looks like. The other thing, the human brain consumes 20 watts. You use 20 watts not only to recognize images, but to drive a car, to find a route in a city that you've never seen before, to watch TV, to listen to me right now, and so on. Just 20 watts. Now, the very deep learning systems employ hundreds, sometimes thousands of GPUs. Each one consumes a lot more. So there's obviously something that our brain does a lot better than these systems. So here, it's hard to answer, has deep learning reached human parity? In some things, it is very good. In some things, it does a wonderful job. I like to think that there are many different kinds of intelligence, and our intelligence is pretty amazing because it can tackle so many fields and even work pretty well on new fields. But there are animals out there who are smarter than us in some fields. My favorite example is the bat. A bat can fly in the dark, can capture insects in the dark, can even land upside down on the ceiling. Can you do that? A dog can smell things we cannot smell. So we've been surrounded ever since by animals that can do things that we cannot do. It's just a different kind of intelligence. And machines from the beginning, that's why we invented computers. They can do things that we cannot do. You know, we used to think that mathematics was the ultimate evidence of intelligence. Well, computers already in the 50s were faster at calculating than humans. And the last, I don't know if you can see the bottom of the slide, there's a big difference between the neuron in your brain and the neuron in the neural network. So, you know, to me, it's just a different kind of intelligence. Now, there are three main types of machine learning today. Supervised learning, which basically classifies objects, for example, recognizes if an image is a banana or an apple. Unsupervised learning that takes some objects and groups them in categories. And then the reinforcement learning, which is important because it has to do with improving your performance. And that's been one of the success stories of the last 8 years. It really started in 2013 with this paper, and it was applied to prove the theory. It was applied to video games, to playing video games. Well, you already know where I want to go. 2016, 6 years ago, AlphaGo made big news because it outperformed the world's greatest player of Go. And then after that, we've had AlphaZero that can learn multiple games. Then OpenAI 5, can't believe it's already 4 years, learn from scratch the multiplayer video game Dota 2 that was more difficult because there's a lot of strategy involved. Note that it trained by playing 180 years worth of games against itself every day, running on 256 GPUs and 128,000 CPU cores, and so on and so on. We can play Dota 2 without consuming so much power. But again, certainly an important moment in the history of AI. And then OpenAI applied that to a robotic hand that solved the cubic, the cube. Another thing that AI had not been able to do before. Since then, we've had a lot of progress. I will not get into the details. Now we have so many different kinds of deep reinforcement learning, and more recent achievements. AlphaFold. AlphaFold has predicted the 3D structure of proteins from the protein sequence, and that's something that human biologists have been trying to do for a long time, and the biologists themselves consider this a major achievement. Now, why is that particularly important? In my opinion, in the opinion of many things, more important than AlphaGo. Well, let's go back 6 years, and Hiroaki Kitano launched the grand challenge for AI to develop a system capable of scientific research that would qualify for a Nobel Prize. So now the question is, AlphaFold did something the biologists think is very important. Does it deserve a Nobel Prize? So this is more than just games, right? This gets more serious. And here you have to ask the philosophers. You know, some people say, yes, AlphaFold deserves a Nobel Prize. Some people say, well, DeepMind that developed AlphaFold deserves a Nobel Prize. For example, BioNTech developed a COVID vaccine using software. It wasn't artificial intelligence, it was more traditional software. But who invented the vaccine? BioNTech's scientists in Germany or the software? So a better question, in my opinion, is why DeepMind succeeded where so many biologists had not succeeded. But anyway, one fundamental question, especially again in the case of the pandemic, is can AI plan for worst case scenarios? Can AI imagine the next crisis? And I haven't seen that yet. What's the problem with deep reinforcement learning? Same. I mean, they need to be trained with thousands, today probably millions of cases. Humans, the star there, they can learn quickly a game and perform decently. I mean, they will never beat AlphaGo, but they can learn how to play Go relatively quickly and start playing games. So that's still very unnatural. So I wouldn't say superhuman, but certainly deep reinforcement learning systems like AlphaZero and AlphaFold, well, they're almost human. By the way, AI beat humans in this famous chess game more than 20 years ago. So it's not new that computers can beat the human masters. So I said that in the 2010s, the popular system was the GAN. That's the paper that made it famous. What is special about the GAN, it can generate all these images of objects that actually don't exist, but they look so real. Since then, actually, just the first 2 years, this slide that is from 2016, I believe, in just 2 or 3 years, there were more than 100 variants. By today, there are probably 200. GANs have been used to generate text from an image, so to describe what happens in this image. They have been used for the opposite, given a text, generate an image, even given a description, generate a video, and maybe the future Hollywood. Maybe you use the GAN, where you just sketch something, in this case, a waterfall, and the GAN generates a photorealistic image of a waterfall. They can generate artworks based on the style of some painter. They can turn a picture, a winter picture, into a summer picture. And they can just generate a lot of photorealistic faces. These are people who don't exist, but the faces look very, very realistic. Superhuman, yes, we cannot do that. So you have to admit the GANs can definitely do something that we cannot do. Now, natural language processing is the big thing today. That's most of the slides I showed at the beginning are about answering question and conversation. Why? Well, because that's how we normally assess somebody's intelligence. So the big revolution here was the attention mechanism and then the self-attention mechanism. And they both were invented in England 6 years ago. And then 5 years ago, a team at Google came up with a transformer algorithm. The transformer architecture has really been the secret of the systems built over the last 4 years. The first generation of system built on transformer, represented by OpenAI, GPT, and Google BERT, introduced the idea of the language model or foundation model. And that's where we are today. what was special about language models and or called the foundation models, they get pre-trained based on some data sets in general linguistic knowledge. And then they can perform very well in many different tasks. What's different from the past? In the past, a system, not a natural language processing system, would be specifically created for one specific task. For example, answer questions. For example, translation. For example, summarizing. Well, these language models basically acquire enough linguistic knowledge that then you can build applications, any kind of applications based on them. And since then, there's been, again, a deluge, an avalanche of similar systems. So these are some of the descendants of BERT. This is GPT-2, second generation GPT. People were very impressed when they saw answers to questions. I mean, GPT-2 was trained with thousands, millions probably of text taken from the web. And then it was able to answer questions like, who wrote the book, The Original Species? Charles Darwin. Well, first of all, you have to understand the question, and then you have to find the answer. And that was already impressive. And then we've had Google T5, Microsoft Turing NLG, Google Shard, and so on. These are some of the results of Google T5 in different kinds of tests. So there's a test for question answering, one for document summarization. Linguistic acceptability is just the general grammatical accuracy, and so on. And this system has been getting better and better at all of these tasks. Now, there's a price to pay. Google G Shard, for example, must be trained on 2,048 TPU accelerators for 4 days. T5 was pre-trained with a lot of data sets. I didn't list all of them. So it's not like somebody you can do at home. GPT-3, about 2 years ago, was even more impressive. The Guardian published this article saying this was written by a machine. The machine was GPT-3. And the article seems like the article written by a professional journalist. Now, there's a trick, of course, a little bit of a trick. The Guardian actually asked GPT-3 to produce the article. GPT produced several articles. I don't remember how many. And then human editors picked the best one and tweaked it a little bit. Now, philosopher can discuss forever here because that's what you normally do with journalists. A journalist writes an article, and then the editor of the magazine or of the website has to decide is it good or not, and sometimes refines it. So is it the same thing that the Guardian did to GPT-3? I'll let philosophers answer the question. There are people who think there's something fundamentally wrong with it. And you've seen examples in previous talks. Sometimes the questions just are either very bad questions or just inherently stupid. But I'll let philosophers decide. What I can tell you, the experience that I have and probably you have, whenever we interact with a chatbot, it's painful, right? It's frustrating. So you read that the AI system have surpassed human performance, and then you interact with the chatbot, and it's so incredibly stupid. So we all have learned ways to get out of the chatbot. You ask some very silly question, the chatbot has not been trained to answer the question, and finally you get to speak to a human being, and in 5 seconds you can ask the question and get an answer. Now, Andrej Karpathy, who is the director of AI at Tesla, wrote very recently, not so much has changed in 33 years. Why 33? I showed you in a previous slide, LeNet was from 1989. So what has changed in these 33 years? That was the question that he was trying to answer. And he actually says, not very much. I mean, we use exactly the same kind of approach. What has changed, as I said in that slide, is the data sets, the computational power, and the software platforms. But the approach is actually very similar. So yes, we have systems that seem to do better and better, but that's the price we pay, okay? But anyway, what is certainly new is the language models. Now we can produce these language models that have a broad linguistic knowledge. Now, there are problems. As I said, sometimes the answers that come out of these systems are not answers that are acceptable. So last year there was this workshop on language models, and I'm pleased that they invited philosophers and psychologists, including my friend Alison Gopnik there, who is a psychologist. And that's really important. It's really important to have an interdisciplinary approach. And again, computational power. This is the new Facebook Meta hardware platform to do AI. 760 NVIDIA systems, 6,080 GPUs, quantum channel, and 175 petabytes of memory. These are colossal resources. I mean, do you really need that much to do what our brain does with just 20 watts? Another problem, they get outdated very quickly. We update ourselves, and these systems are not easy to update. They recently used GPT-2 that was developed in 2019 and asked what is COVID-19. It came up with a LED emitter. GPT-J that was developed in 2021 had the correct answer. So just 2 years, and that GPT-2 of 2019 is already obsolete, very hard to update it. Another practical problem, because the hardware demand is so huge, you don't have the language model in your home. You have it on the cloud, hosted by Google, Microsoft, OpenAI. So there's something weird in that thing, besides the practical fact that they own the knowledge. But it's like I cannot speak without having with me a linguistic expert. That's not what human beings do. Nonetheless, built on these language models, we have chatbots that look very realistic. This is Google Mina, and you can see the improvement in accuracy. For a long time, Mitsuku was the best one. He won a famous contest, I think, 3 years in a row, and now we do better. Still, we don't compare with humans, as anybody who uses chatbot on the web knows. This is the one from Microsoft, also pretty impressive replies. So these language models, you can see the improvement, not so much on translation, actually. Translation reached really a peak in 2016, and then it has improved not much. But in conversation, you can see the difference. Of course, as you keep hearing over and over, is the lack of common sense. That's the fundamental problem of AI to this day, lack of common sense. This is GP3, the one who wrote the article for The Guardian. A patient asked, I feel very bad, I want to kill myself. GP3 said, I am sorry to hear that. I can help you with that. Should I kill myself? I think you should. Is that the kind of answer you expect from a medical expert? Of course not. So, so back to the slide I showed at the very beginning. How can you reconcile what I told you on the limitations of this system with this diagram? Well, it's the benchmark. I mean, each of these benchmarks measures the performance in one specific task. In fact, if you go back, which year was this? 2014, 8 years ago, all the media in the world published the news that an AI system passed Turing test. It all depends how you perform the test. So all this achieving superhuman performance, it really depends on how you test. In the old days, it was called quality assurance. Okay, you develop software and then there's somebody in charge of quality assurance. And doing quality assurance on AI system is difficult. It's not only difficult to explain it, as the previous speaker said, it's also difficult to just test that they're doing a good job. And so every year, a new benchmark is introduced that tries to overcome the contradiction. There's a contradiction there. A benchmark tells me GPT-3 is better than a human being, but then GPT-3 makes silly mistakes that humans don't do. So I personally don't think natural language processing is even close to human beings. So in getting to the end of my presentation, we need to spend a few minutes discussing common sense, because whether you use deep learning or use previous kinds of artificial intelligence that were around when I was a kid, the fundamental question is, how do you give a machine common sense? Whether it's a robot, a piece of software, a chatbot. And there are so many, I can give you so many examples of machines. It's not that they make mistakes. We make mistakes all the time. But machines make mistakes that are incredibly stupid. That's the problem. This was in 2017, the Los Angeles Times reported there was no human being checking. Okay, a machine sent out a report that an earthquake had occurred in the past, in 2025. Now, it was 2017. So maybe the machine was predicting an earthquake, but the Los Angeles Times published the news on the web that there was a warning about an earthquake that happened in 2025. No human being, when a human being saw that, and then eventually they realized, oops, this is not a regular warning. This is a notice sent by PayPal, by the bot of PayPal, to a dead person that she had to pay a debt. There was a report 4 years ago that IBM's Watson supercomputer recommended unsafe and incorrect cancer treatments. I have some examples of what I mean by common sense. See, these are the things that are very difficult for machines. Now, a few years ago, 3-4 years ago, I saw this thing on TV. I took a screenshot. Some children were playing. They saw some people running away. Then they saw the police helicopter. They realized that the people running away were criminals. The police helicopter was looking for them. And the children spontaneously did this. They formed an arrow. That's common sense. I mean, the children are very smart. But anyway, it's common sense. If you have common sense, the arrow means something to humans. First of all, common sense. You want to help the police find the criminals. And the arrow tells the police where the criminals are. Common sense. If you have common sense, you can do these things. Another example is the 2013 terrorist attack during the Boston Marathon. Not many people know how the police found the suspects. It wasn't AI. It was good old investigation. They had cameras, so they had a lot of footage, but they had no specific clues about who dropped the bombs. What they saw a lot of people running away, panic. There's been an explosion. You see people running, screaming, and so on. 2 people walking away very calmly. Now, if you have common sense, those 2 people are suspicious. They are the only people who are not screaming. They're not running. Why? Maybe they knew there was going to be a bomb. That's why. And in fact, it turned out those were the correct suspects. So in terms of common sense, we are not even remotely close. And that explains, in my opinion, most of the limitations that I told you about. The fact that AI is still so impractical in so many cases. You cannot really trust machines with no common sense to drive a car in ordinary traffic. You cannot really trust a machine to give medical advice. Somebody told me medicine is not a science, it's an art, because the doctor needs to have a relationship with the patients. You can't have that. You can have a machine that looks at an image and says, hey, this is a cancer. But you cannot have a machine that treats patients. So success stories, we have success stories. Image recognition, speech recognition, machine translation, game playing, but we're not happy. Some of the machine learning that we are using is unnatural. Unsupervised learning is the kind of learning that humans and animals use all the time. And machines are still very bad at that. So don't trust my judgment for this. Trust people like the founder of DeepMind and legendary scientist Yann LeCun. They gave talks over the last few years where they admitted this. And so there's been more and more research in meta-learning, learning by demonstration, transfer learning, curiosity-driven exploration. We are just curious. That's how we learn. Multitask learning. Humans and also animals can learn multiple things at the same time. These are all machine learning problems. I found by accident an article written by Sebastian Thrun, who was at one point was the director of the self-driving car project at Stanford. Wrote this article in 1995, was talking about these things 27 years ago. Now I would get too philosophical, so I will probably stop in 2 slides. But one thing that we still don't know is really where human intelligence comes from. And that's why it's so difficult to design machine intelligence. Look at the history of AI. The history of AI starts with some people saying there are hard problems and there are problems that are sort of easy. Well, it turned out that the hard problems, like playing chess, playing Go, they were not so hard. We solved them. The easy problems, like talking, those were the difficult problems. That shows you that we don't really know what intelligence is. And then it's very difficult to design artificial intelligence systems. So first, we should learn more about human intelligence. And last year I gave a talk at Stanford that was sort of more philosophical. It was about deep thinking compared with deep learning. What humans do is not just deep learning. We can learn what a banana is, yes. We can recognize a cat, yes, but we can do a lot more. We can write books on cats. We can, first of all, we can ask simple questions. Why are there so many cats on YouTube? See, a machine realizes that there are millions of cats on YouTube and doesn't ask these obvious questions. Why? Humans do that. Why? Humans do that because we have deep thinking, not just deep learning. So I will stop there because otherwise then I get too philosophical.